this section, we're going to discuss the techniques for finding derivatives. Another way to describe this is that we're going to learn some basic rules for finding derivatives. The limit process, as we've seen, is kind of complicated and long and tedious. Just imagine if we had just imagine if we had a function like this. Imagine that f of x, let's say, is 3x to the 7th minus 5x to the 6th, 5x to the 6th power, plus 24x to the 3rd power, plus 2x minus 17. And someone said, find f prime of x. When we start beginning to think of that, we understand that to find f prime of x, that's a limit as h approaches 0 of the fraction f of x plus h minus f of x, all divided by h. And we've seen that four-step process. The very first thing we have to do is to calculate f of x plus h. That's kind of step one in the process, isn't it? Now imagine when we do that, look what that would look like. We would have 3 times x plus h to the 7th power minus 5 times x plus h to the 6th power plus 24 times x plus h to the 3rd power, and then of course we know there's more to this. But can you imagine trying to find x plus h to the 7th power? Probably if I asked you to do that, every one of you would go drop the course right now. So that's what this section is about, is how can we do this without using the limit? So we might also label this section, find the derivative without using a limit, or the limit, other than the limit definition. And that's really what we're talking about here. Previously, is we're using the limit definition of the derivative. Before we get started completely, there's some notation that we need to be familiar with, because we'll be using some new notation about derivatives here. So let's assume once again, let's assume that we are given a function. And just as a simple example, we'll let f of x be equal to x squared plus 3. Now we recognize that we can also call that y is equal to x squared plus 3. So that's an alternative way of writing a function, we understand. Now, the derivative, we've already seen one way to illustrate the derivative of that function. Okay, so the derivative of f of x. Well, one way to write that is just to say f prime of x. That is an all right way. That's the only way we know of now. Now, there's occasionally, if our function is just given to us as a y equal, then sometimes instead of saying f prime of x, we'll say y prime only. But another technique that we'll see that is important is we'll use a language that it looks like kind of a fraction. And we have a d in the numerator, and we have a dx in the denominator. Now the d in the numerator is read the derivative of. That d alone is read the derivative of. And then over here, we tell what we're taking the derivative of. So, for instance, in this example, we were taking the derivative of the original function f of x. So the d in the numerator is derivative of. We see what we're taking the derivative of f of x, and the denominator is read with respect to x, which is just referring to the variable that we're dealing with. If it would have been y is equal to t squared plus 3, then we would have the derivative with respect to t. So we'd have a dt instead in the denominator. And an additional way yet, well, is, let's come up here. An additional way yet is when we're not even knowing, we don't even have the f of x in function notation, we just want to say find the derivative of x squared plus 3. So you find the derivative of x squared plus 3 with respect to x. And then one last notation that we'll see once in a while that is related to the one on the bottom here, we might say the derivative of y with respect to x. But usually that's written as dy over dx on top. And so when you see that, we know we're just talking about the derivative of y with respect to x. Well, there are four basic rules of finding derivatives that we'll look at on the next page. As I said, we have actually 4 rules for finding derivatives, so we're going to begin doing that now. The 4 rules: 1 is the constant rule, 2 is the power rule for finding derivatives, 3 is the constant times a function rule, and the 4th is the sum or difference rule for finding derivatives. Now, each of these will have their own variations. We'll look at a rule, and then we'll look at several examples that go along with that rule, and we'll put it all together at the end. So let's begin with the constant rule. And the constant rule refers to if our function is just a constant function. So for instance, if f of x is a constant function, that means it's just equal to some number, and as it says here, where k is a constant, meaning it's just a number, it's no variable in this, then the derivative of f is equal to 0 alone. That's all there is to it. Now, first, let's just imagine an example of this. Let me write it a different way, and I'm going to maybe abbreviate this in the future. So I'm going to say if f of x is equal to k, that implies that f prime of x is equal to 0. That is, the derivative of f is equal to 0. Now, another way to write this with that new notation would be the derivative of k with respect to x. So that is, the derivative of a constant with respect to x is 0. That's saying exactly the same thing above. It just says it without the function notation. Now, in this one case, and we're not going to do this in the future, but in this one case, I'd like to show you kind of a proof of this idea, a proof by example, okay? And you'll see that it's really pretty simple. In fact, a couple of things about it. But let's assume that we were finding f prime of x by using the limit notation. That is, it would be the limit of f of x plus h minus f of x divided by h as h approaches 0. Now, in this case, remember, the f of x is just some constant. So we'll just pick on 5 for right now. Let's assume f of x is equal to 5. So when we go over here to start thinking about finding this limit, what we would have is that f of x plus h we would need to calculate. Well, the function f of x is 5 regardless of what we're finding the function value of. In other words, f of 3 is 5, f of 2 is 5, f of 7 is 5, f of x is 5, and for that matter, f of x plus h is 5. So that would have been the first step. Now, the second step is to find f of x plus h minus f of x. But f of x plus h is 5, and also f of x is 5, and so we have 5 minus 5, or 0. And so, of course, when we calculate the fraction, f of x plus h minus f of x divided by h, we end up on top with a 0, on bottom with an h, but that fraction will just be 0. And then our next step, you recall, would be actually calculating that limit. And in this case, we would have nothing more when we replace that fraction with its value. We'd have nothing more than the limit of 0 as h approaches 0. But it really doesn't matter that h is approaching 0 here, because it's the limit of a constant. And remember, the limit of a constant is always 0. And so in this case, we get 0. And it really wasn't important that f of x was 5. If f of x was a constant, then we would get that constant in both of these positions, and so the numerator would always be 0. Now here's another way to look at this. Remember what the graph of f of x would look like if f of x is 5. See, if f of x is equal to 5, then the graph of that is really just the graph of a horizontal line. See, that's the horizontal line, y equals 5. And so if we were making this graph, let's say 1, 2, 3, 4, 5, 6, and so on. Here's where 5 is. We'd have a horizontal line that goes through 5, but more importantly now, what we're asking for is the derivative. And remember, f prime of x represents the slope of the tangent line. Anywhere on the graph, well here, anywhere on the graph, here's an x, there's a point on the line, and of course the tangent to that would be the same line. To be tangent, we would have to go through the same line, wouldn't we? So the tangent line, no matter where we are, is a horizontal line, hence the slope of that tangent line is 0. And so once again, we can see that the derivative of a constant function is just 0. Well, again, on the next page, I went a little further on this than I normally would. On the next page, we'll look at a couple of real simple examples. Okay, with this constant rule examples. So the first one, for instance, let's just say f of x is equal to 7. Then that tells us that f prime of x, of course, is just 0. It's almost meaningless, isn't it, here? Or suppose we had g of x is equal to negative 1/2. Well, and someone asked us to find the derivative of g prime of x will be 0 because the function itself is just a constant negative 1/2. Or likewise, we might be asked for the derivative with respect to x of the number 1. Well, we're taking the derivative of a constant, and anytime we take the derivative of a constant, we get 0. Or we might ask, just to throw things in here a little bit differently, the derivative of x, the derivative of pi with respect to x. Well, pi is a constant. Although we write it in a funny way, it's just a constant number, no variable at all. So once again, we would get 0. And those examples get boring very quickly. The next rule is a very, very important rule, and probably the one we use the most, and it's called the power rule. Now, the power rule is about finding derivatives of functions that are x to a power. So, for instance, let's write it this way: if f of x is equal to x to some power n, okay, some power n, then the way we find the derivative, that is f prime of x, we do this mechanically. We take the original exponent that's on n, and we write that in front of x, on x. So we take the original exponent and write it in front of x, and then we create a new exponent for x that is 1 less than the original. So we take the original exponent in and subtract 1 from it to get the new exponent on x. Now, again, another way to write this in the notation, the way I showed a while ago, that if f of x is equal to x to the n power, then that implies, of course, that f prime of x is equal to n times x to a power that is 1 less than the original exponent. So original exponent times x to an exponent 1 less than the original exponent. Or, in this d notation, the derivative of x to the n power with respect to x is n times x to the n minus 1 power. So again, let's look at some examples that go with this power rule. And there's a wide variety of examples here. We'll start out with some very simple ones and straightforward ones. Suppose f of x is equal to, well, let's just say x to the 5th power. Okay? Then f prime of x is going to be, what do? We take the exponent, original exponent, and write it down, and then we have x to a new power that is 1 less than the original exponent. Well, 1 less than 5, of course, is 4, so the new exponent's 4. Wow, that's easy. Or if we had g of x is equal to x to the, well, let's say the, I don't know, this is almost too simple, isn't it? The 2nd power. Well, then g prime of x will be what? We take the exponent down, so that's a 2. We times x with a new exponent that is 1 less than the original. Well, 2 minus 1 is 1, and so we probably won't even write that in most cases. We wouldn't write that exponent 1. We would just write 2x. Aha. Now, I'd also like to point out that sometimes we're given a function in another variable name. It might be f of t is equal to t to the 7th power. Well, then if we're asked for the derivative, it would look like f prime of t, and of course that would be 7 times a t, not an x, to the 6th power in this case. Now, here's a special case, a special situation, and that is when the function is just x itself. That is, for instance, f of x is just x. Well, in this case, here's what would happen. F prime of x, what we would have to remember is that the exponent that we see on this x is really a 1. And so when we bring that 1 down, then the exponent that we would have on x would be 0, 1 minus 1. And then we have to remember that x to the 0, or any number to the 0 power, is just 1. So in this case, we get 1. That is, real simply, the derivative with respect to x of just x is a single 1. That's all we get. Or the way we said it before, f of x equal x implies f prime of x is simply 1. Now, again, these are pretty straightforward, but the special case is important, and that's something that we need to get into our mind. But there's some other examples that we need to look at that we might not think of originally. So we'll do that on the next page. Continuing with the power rule, let's look at additional examples. Okay, so for instance, suppose we're given that f of x is equal to, let's say, x to the negative fourth power. So, a negative exponent. Well, that didn't say that we couldn't have negative exponents. Then find f prime of x. Well, here's the way we would go about that, of course. F prime of x, what do we do this time? Well, of course, the exponent's negative 4, so we bring it down, and then we create a new exponent on x, and that new exponent, we have to be careful. It's the old exponent subtract 1. Well, negative 4 subtract 1, of course, is negative 5. So the new exponent is negative 5. Now, I hope we understand that we're normally not going to be dealing with negative exponents in this fashion. We don't really like to leave our answer with a negative exponent, although the original function was given that way. So we would probably rewrite this so that we had the negative 4, and remember that x to the negative 5 means 1 over x to the positive 5. And so our final result would be negative 4 times that fraction, which we would write as negative 4 over x to the fifth power. Now, that kind of leads us to the next type of problem that we might encounter. And this time we're given f of x is equal to 1 over x to the third power. 1 over x to the third power. And we're supposed to find f prime of x. Now, a common mistake here is to apply the power rule first. And the power rule doesn't say what happens when we have 1 over x to a power. It just tells us what we do when we have x to a power. So the power rule does not apply yet. See, the power rule does not apply. It does not apply yet. And the reason I'm saying that once again is for the power rule, we're taking the derivative of x to a power not 1 over x to a power. It didn't tell us about that. And that's what we have. So this is a common thing that we do in calculus, that before we do the work, we use a little bit of algebra to rewrite things in a form that will allow us to work with them or use a rule we know. Now, we know from algebra that 1 over x to the third could have come from x to the negative 3 power. And that looks more like what we had up above. And now the power rule applies. See, that's the important part. Now the power rule applies because we simply have x to a power. And that's an important point again. So at this stage, after we rewrite, after we do this algebra, we'll be able to find the derivative like we did above. We'll bring the negative 3 down. We'll say negative 3 times x to a new power. Well, the new power is negative 3 subtract 1, which is a power negative 4. So we would get a negative 4 power there. And because we'll not leave this with negative exponents, we have to come and now do some more work to say, oh, well, that's really negative 3 times 1 over x to the positive 4 power. And so we'll conclude then by writing that as a single fraction, negative 3 over x to the power 4. That's the result of what we were working on. So that's a little more complicated than we would have imagined. Now this next one also is something that we might not realize that this power rule gives us the capability of doing. This time, let's suppose the function that we're given is the square root of x. F of x is the square root of x. And we're to find f prime of x. Okay. Well, we don't have a rule that tells us what to do with square roots. There's no rule about that, and we're looking at the power rule versions. So the power rule does not apply here either. But if we remember that we can do some algebra, we can use an algebraic technique that we can really rewrite the square root of x as x to the power 1/2. Now, once we recognize that, all of a sudden we know, oh, the power rule really does apply. We just had to look at it differently. Now, after we've done that, now we can find the derivative. We just rewrote the function f, but now we can find the derivative because the power rule applies. So we bring the exponent 1/2 down and say x to a new exponent. Now, the new exponent we calculate by taking 1/2 and subtracting 1. And we ought to be able to recognize pretty quickly or calculate that that will give us a negative 1/2 result. So the new exponent is negative 1/2. Now we have the same issue as we had above. We can't leave a negative exponent, so we stop and think about how we can rewrite this so we don't have a negative exponent. And the negative exponent only affects the x, so this is 1 over x to the positive 1/2 power. And then we say, oh yes, x to the 1/2 power is really a square root. And so we rewrite this as f prime of x is 1/2 times 1 over, replace x to the 1/2 with square root of x. And then we finally recognize that, of course, we can write that as one fraction. That's 1 over 2 times the square root of x. Because when we multiply fractions, we multiply the ones together on top, and we multiply the denominators together on the bottom. So this is actually the result that we would get there. So we see here the same situation that happened above. That to the original function, the power rule did not apply. So the power rule didn't apply when we looked at this. And so we used a little algebra to reformat so that the rule does apply. After we did that, so we used some algebra to manipulate so that we could use the power rule. After we did that, then we found the derivative, okay, and that was pretty simple. Then we found the derivative, and then we spent the rest of the time using algebra again to get it in a better form. And that's not going to be an unusual situation. Use some algebraic techniques, finding the derivative is easy, then we have to spend some more time using additional algebraic techniques. Let's do one more example of this on the next page. We'll see this happen again, and then we'll look at the new rule. We're going to look at one more example here of the power rule. This time we'll be given this function. Let's say given f of x is equal to 1 over the cube root of x. And we're supposed to find f prime of x. I mean, can you even imagine, even thinking about how we would attempt this if we were dealing with the limit definition of the derivative? But now that we've got this rule, this power rule, or we're developing these rules, this won't be too difficult if we're decent at algebra. So again, the power rule doesn't apply directly, so we take the function f of x, just been kind of putting things down here, and we have to think in pieces. We already know that cube roots can be written as fractions, so we'll rewrite f of x as 1 over, instead of the cube root of x, x to a power of 1/3. But we still know that the power rule doesn't work here, because the power rule isn't about powers in a denominator, it's about x to powers in a numerator. So we have to do one more thing before we think about finding the derivative, and that is we write 1 over x to the 1/3 as x to the power negative 1/3. Now we finally have f of x written as x to a power. It is now that we're worried about finding the derivative. We've done all that work, and now we can use the power rule directly. We bring that negative 1/3 fraction or exponent in front of the x, and so we write x to a new power, but we have to calculate that new power. And that'll be negative 1/3 subtract 1, which is negative 1/3 subtract 3 over 3, which is negative 4/3. Is that what we would get? Negative 4/3? I believe so. Double check me? I believe so. So our new exponent is negative 4/3. Now we won't leave a negative exponent. That's not something that we normally do. So we'd need to use algebra again to rewrite, and we'd say, oh, well, that's negative 1/3 times 1 over x to the positive 4/3 power. Okay, and then we recognize, well, we can multiply those two fractions together. We're going to have a negative fraction because it's negative times positive. On the top, we'll have 1 times 1, which is 1. On the bottom, we'll have 3 times x to the 4/3 power. Now, I might, this might be the stopping place. Okay, that might be our result. I do want to point out, though, before we move from here, x to the 4/3 power. Okay, x to the 4/3 power can be written a little differently. X to the 4/3 power, remember the 3 in the denominator of the exponent means a cube root. So this is really the same as the cube root of x to the 4th power. Now, this is an example also of something that whenever the exponent underneath the radical is greater than the index of the radical, it means we can simplify. So if you recall, this could actually be written as, let's see, the cube root of x cubed times x. X cubed times x is x to the 4th. And we can take the cube root of x cubed, that's just x. So we would have left under the radical only an x. So x to the 4/3 is the same as x times the cube root of x. So that would tell us that we could rewrite this as negative 1 over 3 times x times the cube root of x. And that would be an alternative form of writing that, and we may run into that on occasion. So we need to be appreciative of that situation. Here we're talking about a new rule, a constant times the function rule, and you can see it stated below that if f of x is a function that is k times some other function u of x, then f prime of x, or the derivative of f, is just k times the derivative of u prime of x. So basically it tells us we can concentrate on the other function and finding its derivative, and just remember to multiply that with k. Another way this could be written with our previous notation that we learned is that if we have the derivative of k times a function u, then the result is k times the derivative of that function u. And once again, this points out more than anything else that we can calculate, or our concentration actually is now finding the derivative of the function u. So let's right now it probably seems like, where in the world would we ever see something like this, because things don't look this way. So here's our first example, and we'll go through several as we have before. Our first example is that we're given a function that is f of x, let's say 3 times x to the 5th power. That's the function. Now the challenge, and we're defined, of course, the derivative. Find f prime of x. So at first thought, this doesn't look like this rule would apply because we don't see any extra functions walking around. But what we really have to do is to imagine the way this thing does apply is that 3 is actually the constant k. And that u of x, that x to the 5th is actually this other function u of x. And so remember what this would tell us then is to find f prime of x, we take the constant, that's the 3, and we find the derivative of the function u. And to find the derivative of the function u here is just finding the derivative of x to the 5th. And then we use the power rule to do that. So we have our constant 3, and then we calculate the derivative of u, which before we know is we bring down that exponent 5, and we put the new exponent 4 on x. So of course, there's the k, and there is the derivative of u. And so together we see that result, of course, that is f prime of x, ends up being 15x to the 4th power. Now we can go through another example, and we'll state this one a little differently. Let's see. Find the derivative asked for by the statement. The derivative of negative 7x cubed with respect to x. So that's what we're supposed to find. Okay, well, let's remember how this goes. We're going to, let me rewrite it. The derivative of negative 7x cubed. So we're thinking of the negative 7 as the constant. That's the k. And so the rule says, well, that's negative 7 then times the derivative of the function. And in this case, we're thinking of the function as x cubed. Now, of course, that derivative is pretty easy to find because we just use the power rule. So we have our negative 7. When we find the derivative of x cubed, we get 3x squared, of course. And then we see that we can multiply those together, negative 7 times negative 3, and so we get the result, negative 21x to the 2nd power. And so our result then, of course, is right here. Okay, let's continue with our examples using the constant times the function rule. So here's the next example. Find the derivative of f, that is f prime of x, if we're given that f of x is 3 divided by x to the power 4. Now, we've already been through this idea that, well, I say we've been through this idea. This may not be clear the steps we need to take, but we're going back to the idea that we need to maybe manipulate before we go any further. So what I want you to notice, if it's not obvious, is that f of x is really 3 times 1 over x to the 4th. We can think of that's what's really happening. And of course, for us to be able to think of 1 over x to the 4th as a function we can take the derivative of, we need to write it in a fashion so that it is x to a power, and so it'd have to be x to a negative power, or negative 4 power. Now we can apply the rules that we need to apply after we consider that. So f prime of x then, of course, we're going to calculate by, remember it's going to be the constant 3, and then we have to find the derivative of x to the negative 4th, which will be negative 4 times x to a new power. Negative 4 minus 1 is negative 5. So that's the result we would get. But of course, there's more work that can be done here because we need to multiply that 3 and that negative 4 together. So the next step we would take is we'd say, oh, well, that's negative 12. And it's negative 12 times x to the negative fifth. But we know we'll never leave a negative exponent, so we clean up a little bit more, okay? Go another step here, and write x to the negative fifth as 1 over x to the fifth. So that's negative 12 times 1 over x to the positive 5 power. And then finally, we would say, oh, well, then that means f prime of x is negative 12 over x to the fifth power, and we finally have our result. So we see that's those steps again. We used algebra, we found the derivative, and then we used algebra. That's not an uncommon situation that we go through this sequence of steps to get to the case that we want to realize. Now, I would also like you to notice here, and we can kind of speed this process up. This is kind of tedious the way we're doing it. Notice at this step that we have right here, that when we, in fact, compare these two steps, when we had f of x is equal to 3 times x to the negative 4 power, and we wanted to find the derivative, then in this next step, we ended up with a 3 times a negative 4, you kind of think of that alone, and an x to the negative fifth. I just kind of rewrote what I have over here on the left side. We ended up with a 3 times a negative 4, and notice what this is. This is the coefficient of x to begin with. See, this is the coefficient right here, and this is the old exponent. So what we really did is we took this exponent and we multiplied that coefficient together to get the negative 12 that was on the next step. And so that's kind of going to speed things up when we look at these other examples. So let's do that here. Let's say find f prime of x if f of x is equal to, let's say, 5 times x to the 7th power. Now, in this case, and this is a simpler case than the other cases, but in this case, if we look at what we just did above, all we're really going to do is multiply that coefficient and that exponent together, aren't we? We're going to think of multiply the 7 and the 5 because ultimately that's what happens. So we would end up with 35. That's the 7 times the 5. The old exponent multiplied together with, of course, the coefficient of x. And then we're decreasing the power by 1. The old power subtract 1 is 6, and so the new power is 6. So we can do that all in our head, was the point. We don't really need to take those extra steps. Okay, I would like to finish this rule with a special case, because this special case is going to come in handy, and it's something that we just want to get used to. So the special case is, what happens if f of x is just some constant times x to the first power, okay? In other words, it might be, in more generally, f of x is just a k times x to the first power. Well, what's going to happen when we find the derivative here is that we're going to say, okay, it's 3 times the derivative of x. But the derivative of x, remember, has an exponent of 1. The x has an exponent of 1. And when we decrease that exponent, we're going to get 0 as an exponent. And so that ends up being 3 times 1 times 1, or just 3. In other words, this part just becomes 1. Okay? This part, that part just became 1 altogether. So the derivative of the derivative of 3x ended up just being 3. More generally, if we have a constant times x, the derivative will just be k. And so that's something that we want to be able to recognize real quickly, that, for instance, the derivative of 10x is just 10, or the derivative of negative 7x is just negative 7. And it's because of the process that we saw above. And that's really the issue here, is we can speed this up, and that's what we want to do. Okay, our fourth and final basic rule is the sum or difference rule. That means we're talking about adding additions and subtractions. Here's the way the rule is stated. If f of x, if our function is the sum or difference of two other functions, so either an addition or subtraction between two functions, then the way we find the derivative, then f prime of x ends up being the derivative of the first function and either plus or minus, depending on what the original sign was, the derivative of the second function. Now, an alternative way to write this, of course, is with this d notation. That is, the derivative of a sum of functions u and x with respect to x is nothing more than the derivative of the first function, plus or minus, I should have said plus or minus, the derivative of the second function. And of course, derivative of the u is, we write that as u prime, and the derivative of v we write as v prime. Now, one other thing before I go here, I know that this is getting long, but sometimes we shortcut because we don't like that of x all the time. So we might say the derivative of u plus v, or plus or minus v, without the of x, is equal to the derivative of u with respect to x plus or minus the derivative of v with respect to x. And of course, we might even shortcut that and just say u prime plus or minus v prime. That might be the way it's written in the future. Well, let's look at our first example. How in the world would this apply? And so the example here is we're given that f of x is the function 3x squared plus 5. We're to find f prime of x, the derivative. And so the real secret for us here is that because of the plus sign we have between these two, that we're going to think of this 3x squared as one function, u of x, plus we have a second function, and we're going to think of it as v of x. And so we just have to find the derivative of u and v. That is, remember, f prime of x is nothing more than the derivative of u plus the derivative of v. And so in this case, we can easily calculate the derivative of u just by looking at it. And we remember, oh, we'll take the exponent 2, we'll multiply with 3, that gives us an x. Okay, and we also remember that we reduce that exponent on x by 1. And we don't normally write x to the first power, so we'll just write x. And then we look over at the function v. And the function v is just 5. And the derivative of 5, that's the derivative of a constant. And the derivative of a constant is 0. So we would just end up writing a 0 there. Or we would, of course, simplify that and say f prime of x is really just 6x. And so we've done that very quickly. Okay, it's not a bad thing at all. I need a little more room on the next page, for the next example, so I'm going to go to the next page. Well, as you can see, this is the continuation of sum or difference rule from the previous page. And the function we're given here is the one that I started out with at the very beginning of this lecture. F of x is 3x to the 7th minus 5x to the 6th plus 24x cubed plus 2x minus 17. And we're to find the derivative. And we were imagining earlier, how would we do that using the limit notation or the limit definition, and it would have been very difficult. This is going to be relatively easy for us. It's going to require that we put all of our 4 basic rules together to do this problem. And the very first thing that we need to notice, although the sum or difference rule was just for two functions. It applies no matter how many additions or subtractions that we have. So in this function, we can actually think of it as 1, 2, 3, 4, 5 functions added and subtracted together. So the way we would go about doing this then is we would say, okay, f prime of x is going to be the sum or difference of all of the derivatives of all of those different functions. And so I'm going to write it out so we recognize what's being done. We have to find the derivative of the first, which is 3x to the 7th, pardon me, and then subtract the derivative of the second, which is 5x to the 6th, and then add the derivative of the third, which is 24x cubed, and then add the derivative of the fourth, so that's the derivative of 2x, and then finally subtract the derivative of the last term, and of course that last term is 17. So when we go through now, we can actually just use the other rules. That's the sum or difference rule. We can use the other rules to calculate each of those derivatives. And so we would see that in this very first derivative that we have here, we'd multiply the 7 and the 3 to get a 21, and we would decrease the exponent to 6. And then we write our minus sign. And then in this derivative, we'd see we'd multiply the 6 and the 5 to get a 30, and we'd decrease the exponent by 1 and get an exponent of 5. And then we would use the plus sign. And now we worry about this derivative. And so we might multiply the 3 and the 24 and find out that that's 72. And we would decrease the exponent by 1, so we'd have an exponent of 2. And then in this derivative, oh, this is that special case, the derivative of just 2x is just a 2, because the exponent on x is 1. That would be 1 times 2. And then we'd have a new exponent on x, which is 0, and x to the 0 is just 1. And so we'd just get a 2 there. And then finally, we'd have the derivative of 17. And remember, the derivative of a constant is always 0. So the final result, we could kind of get rid of that 0, would be 21 x to the 6th minus 30 x to the 5th plus 72 x to the 2nd plus 2. And that was pretty easy after all, as long as we didn't have to use the limit notation. Now in practice, I probably wouldn't have written out all those derivative ofs, derivative of. I probably just would have looked at the original function way up above, and I just would have thought about how do I do to get that derivative, and I would have written it in here. Then I would have looked at the second term, thought, how do I get that derivative, and I would have put it in here, and so on, rather than write out the steps that I wrote here. This is to explain how it was done. Now, next we're going to go back to an application type problem where we're going to find the slope of the tangent line and find the equation of the tangent line, but now we have new ways to find the derivative. And so that's what we're going to do on the next page. Okay, an application of these new rules, using the basic rules for derivatives to solve this problem. So we're given a function y equal negative 3x to the 5th minus 8x cubed plus 4x squared. And we're to do two things. Find the slope of the tangent line at x equal 1, and then find the equation of that tangent line at x equal 1. So as we start on part A, you know, we are asked for a slope of the tangent line. And we remember earlier that the way, that's what the derivative is. The derivative is a generator, is something that tells us how we can calculate the slope of a tangent line if we know the x value that we're tangent at. So here is our situation then. Before we had to use a limit to find the derivative, but here we don't. And so what we need to do to find this slope, we need to find the derivative of y with respect to x. Now remember, that's another notation. And after we find that derivative of y with respect to x, we need to actually put the value x into that derivative. And so that's the way we'll write this. We'll evaluate it at x equal 1. So our job is to find the derivative of y with respect to x. Now, we look above and see that the way we can do that, we remember just from a few minutes ago. We look at the first term, negative 3x to the fifth, and we find that derivative. So we multiply the 5 and the negative 3, that gives us a negative 15. We reduce the power on x by 1, so we get a power of 4. And then we have the next minus sign above. And we're taking the derivative of 8x to the third. Well, we multiply the 3 and the 8 together, and we get a 24. And we reduce the power on x by 1, so we can get a new power of 2. And then we look at the next term. We have a plus sign. And we look at the derivative of 4x squared. Of course, the derivative of 4x squared, we multiply the 2 and the 4, and we get 8. And we reduce the power on x by 1, and that would just be x to the first power. So earlier, that was a long process. We'd have to use the limit, but now we can do this very quickly. So here's where we are. We have the slope then is this derivative of y with respect to x evaluated at x equal 1. So what that means is we put a 1 in for all of the x's. So I'm just replacing all the x's with a 1, and we calculate. And so what do we get here? That's a negative 15 in the first position, a minus 24 in the second position, and plus 8. And I believe if my calculations are right, well, negative 15 minus 24 is negative 39 plus 8, and negative 39 plus 8 is negative 31. So the slope, when x is equal to 1, the slope of the tangent line is negative 31. Okay, well, that's the answer to part A. Slope is negative 31. Now, the part B is that we need to know the equation of the tangent line at x equal 1. But now, remember, to find the equation of any line, the equation of any line requires two components. It requires a slope of the line, and 2, a point on the line. And we have a little trouble here because we don't know a point on this tangent line. Now what we know is that we have the point of tangency, that is, the point of tangency, that is, we're talking about the tangent line when x is equal to 1. And so we know when x is equal to 1, we have a tangent line going through a point, and we also have the graph going to a point. That is where the two places are together. So for instance, we have a graph, and we have a tangent line, and what we know is this is happening when x is equal to 1. That's what we know above. And so that point, when x is 1, is on both the graph and the tangent line. And that's important for us to decide what a point on the line is. Now, that point on the line and the point on the graph match. So if we know x is equal to 1, then the way we would calculate y, although we're not using the line, we're using the function, we would calculate y by putting 1 into the original function. So that's how we would know what that point is. So our y value here is negative 3 times 1 to the 5th power minus 8 times 1 to the 3rd power plus 4 times 1 to the 2nd power. And of course, when we do all those calculations, we'll end up with a negative 7. So now let me reiterate here. The point where x is 1 and y is negative 7 is on both the tangent line the tangent line, whoops, and the graph. See, it's on both of those because that's where we're tangent. So we've satisfied the two things above. That we knew from earlier that the slope was negative 31. That's what we did in part A. And now we know a point. We know a point that is on the tangent line, and that's 1, negative 7. So we have both of the pieces of information we need. Now remember what we do then is we use the little formula y minus y sub 1 is equal to m times x minus x sub 1. And this is depending on the fact that we know the m value, which is the slope, and the x sub 1 and the y sub 1 are a point that are on the line. So we fill these in. We would have y subtract the y value that we know is on the point, which is negative 7, is equal to our slope m, which is negative 31, times x minus the x value of the point that we know is on the tangent line and the graph. And so we go about simplifying this. Let's see, let me move up over here. Y subtract negative 7 is y plus 7. And then we have a negative 31 times x, and a negative 31 times negative 1 ends up being plus 31. And then we would subtract 7 on both sides. So we would end up with y is negative 31x plus 31 subtract 7. And of course, when we subtract 7 from 31, we end up with 24. And so the slope of our tangent line is y equal negative 31x plus 24. I want to finish this section with a pretty interesting problem. We're going to find places on a graph with a specific slope, not find the slope of. We are given a slope, and we want to know where the graph has tangent lines with that slope. So that's on the next page. Okay, here you see the statement of the problem. At what point or points on the graph of f of x equal 2x cubed minus 9x squared minus 12x plus 5 is the slope of the tangent line 12? Now, we don't really know what this graph looks like, but let me just kind of illustrate, and I'm not claiming that this is the graph. But let's kind of illustrate what this is about. Now, because this is an x cubed graph, we've seen previously that it may not look this way, but it's not unreasonable to expect it to look like something that has a couple of humps in it, like this. Okay, so that's not, and we know the orientation being that the left end is going to go down and the right end is going to go up. Now, what we're doing is looking for places on the graph where we have a slope of 12, a tangent line that has a slope of 12. And so I'm just kind of, in this case, I'm just kind of making an observation, and not that it's necessarily the case. But suppose right here is one such tangent line. I mean, certainly this would be a place where we have a tangent line that's pretty steep. And now if we looked in this part of the graph, those tangent lines would end up being negative, wouldn't they? So we couldn't have one there, but we might have another one over here someplace that has a tangent line that is 12. So we've got, it has a slope of 12. So it's reasonable to expect that we might have two different positions on the graph. Now, how we approach this problem is that we remember that the derivative is a way we calculate slopes of tangent lines. See, that's what a derivative does. The slope of the tangent line is calculated by using the derivative. Let's keep that in mind. So those are synonymous, basically. Slope of a tangent line. So that really tells us that what we're looking for is a slope of 12, and so we're looking to find out when the derivative is equal to 12. The slope is 12, and the derivative calculates the slope, so we want to know when the derivative is 12. So our very first job then is to figure out what the derivative is. And of course, before today, that would have been difficult. But now we can find the derivative of that function rather rapidly. We look above, the derivative of 2x cubed is 6x squared. 3 times 2 is 6, reduce the exponent by 1. Minus the derivative of 9x squared, 2 times 9 is 18, reduce the power on x by 1, we have x to the first power. The derivative of negative 12x, or minus the derivative of 12x, well, of course, the derivative of 12x is just 12, so we've talked about before, and then plus the derivative of 5, and the derivative of a constant is always 0. And so our derivative in simplified form is 6x squared minus 18x minus 12. Now, we want to know when the derivative is equal to 12. See, that was what we decided up above. And so that's just asking the question, when is 6x squared minus 18x minus 12 equal to 12? That's now the question. Okay, derivative equal 12. Well, that means we need to solve an equation, don't we? We've got to solve this equation. And to solve this equation, we recognize that it's a quadratic equation, so we need to get all terms on one side. We need 0 on one side. And so we end up taking the 6x squared minus 18x minus 12 side and subtracting 12 from it and 12 from the right side, so we end up with 0. But we have a negative 12 minus 12 on the left side, which is negative 24. So this ends up being 6x squared minus 18x minus 24 is equal to 0. Now we see that we have a quadratic equation we can solve. We can either, to solve this, we have two options. Quadratic formula, I'll always solve one, but that's kind of long and tedious. Or, if we can factor it, we could do it by factoring. But because, by factoring. But because we have such large numbers here, that's going to be kind of tedious factoring. Now, what I'm noticing is that if we look at every term, we have a 6, we have an 18, we have a 24, all of those are divisible by 6. Why don't we divide both sides by 6 so that we can reduce the complexity of the problem, of the equation? So we'll take the left side and divide it by 6, and we'll take the right side and divide it by 6. Now, what really happens when we divide the left side by 6, we are actually having to divide every single term by 6. And we might have just written that originally, but that's what we're going to show now. And of course, we still have 0 divided by 6 here. So probably what I would do in the future is I would have just taken this step. Now 6x squared divided by 6 is just x squared. 18x divided by 6, of course, is just 3x. And 24 divided by 6, of course, is just 4. And of course, 0 divided by 6 is just 0. So now this is a much simpler problem for us to solve, and we'll continue it on the next page. What we're working on now is solving x squared minus 3x minus 4 equals 0, and we can easily factor this, I believe. In this case, what would we have? How about x plus 1 times x minus 4? Double check me there, but I'm pretty sure that's right. And so we can easily see that the solutions here are x equal negative 1 and x equal positive 4. But are we done? And I claim no, we're not done, because the problem was what points on the graph, how was it stated? Yeah, what points on the graph of f of x is the slope of the tangent line equal to 12? And what we've done is find the x values of the points. See, those are the x values of those points. We need to know the points. Now here's what we know, that we have 2 points. One of the points has an x value of -1. We have to find the y value. And of course, the way we find that y value is we put -1 into the function. And the second point we know has an x value of 4, but we don't know its y value. But the way we find its y value, the y value, is we put the x value 4 into the function. So after we do, let's go ahead and do that. F of -1, if you go back and look at the original function, is 2 times x cubed, so that'd be -1 cubed, minus 9. Now this is the function, the original function, not the derivative, not the derivative. We're looking for points on the graph of the function, not necessarily points that are on the derivative. But anyway, so on the tangent line, pardon me. So it was -9 times x squared, and so x is -1, so we'd have -1 squared. And it was -12 times x, and x is -1, and then it was a +5. And when we do those calculations, we'll end up with a -2 here, and a -9, and a +12, and a +5, and altogether that becomes 6. And similarly, we would do something with the value 4, x equals 4. That would be 2 times 4 cubed, minus 9 times 4 squared, minus 12 times 4, plus 5. 4 cubed is 64, and 2 times 64 is 128. 4 squared is 16, and 9 times 16 is 144. And of course, 12 times 4 is 48, and plus 5. A little bit of calculation here. We'd get 133 minus 172. That's the 128 and the 5 added together, and the 144 and the 48 added or subtracted together, and that ends up being -39. And so now we can conclude the points where the tangent line has a slope of 12 are at -1, 6 and 4, -39. Remember how we did this. This is an important problem. Well, that's the end of this lesson. I hope it's been helpful. I know it's long, but I hope it's been helpful.